So we have one more lesson in this unit. We have a test next, not next class, but in 2 classes. Okay? And this last lesson is more kind of refreshing on our algebra skills to find limits, limits being the new calculus concept. However, the calculus concept was the whole idea of getting really, really close to something and approaching something. Okay? This is more just kind of general reviewing some of our techniques, our skills from previous years. Okay? And before we do these 3 limits, let's just look at these 2. If I asked you to find really a limit of any function, not just a trig function, the first thing you should do is try to find that function value. And if the function value exists, guess what? That's your limit. If I ask you to find the limit as x approaches pi over 4 of secant of x, first thing you should try to do, plug in pi over 4. Secant is the reciprocal of cosine. Cosine of pi over 4 is root 2 over 2. This is 1 over root, so this is 1 over root 2 over 2, or 2 over root 2, which is root 2. Okay? And if I ask you to find the limit as x approaches pi over 2 of sine x over x, you would just find that it's the sine of pi over 2 over pi over 2. Sine of pi over 2 is 1. That's 1 over pi over 2, which is 2 over pi. Okay? Always your first step. Plug it in. However, for these 3, if I tried to plug in 0 for all 3 of them, I'd get 0 over 0. I think you still have some music on. Now, when you get 0 over 0, that does not mean the limit does not exist. That's usually an indication that the function has a hole and that we are approaching the location of that hole from left and from the right. But if we look at these and we try to algebraically simplify them, it's not obvious what we should do. It's actually something where we just can't figure this out algebraically. Instead, I will use my calculator to figure out. So let's just look at sine x over x. If I look at 0, we see we are not approaching a specific y value. The y value is undefined. That's that 0 over 0 showing up. However, we can see on the graph right around 0 that there is some value that we're approaching. It appears to be at 1. If I press trace and kind of look to the left and to the right, I can see that we are, yep, looks like we're close to 1, and I could do a little bit of further inspection, type in 0.0001. We essentially, the calculator is rounding here, but they're telling me that we are located at 1. Okay? So this limit is simply 1. It turns out, so this one ends up being 0. Now, the 3 of these we are going to use as a tool to find certain trig limits, okay, where we have trig functions. But in particular, out of the 3, we will use this one more than the other 2. The other 2 you may use if you are working through the homework problems or through the review. However, this one we must just know. Okay, that the limit as x approaches 0 of sine x over x is 1. And we'll call this a tool to help with other limits. All right, we need some more tools that will help us with these trig limits we're about to do. These may seem obvious, but it's important to be stated. If we're trying to find the limit of two functions being multiplied together, we can just multiply the two functions separately and their limits separately, like that. The limit of f times g is the same as the limit of f times the limit of g. If I have a constant, we'll call this k a constant, just a value, times a function, we can actually just pull out the constant, multiply that constant by the limit of the function. Okay, so that's another tool that we will use to find these limits. Another thing we will use is our friend multiplication, and understanding that multiplication is commutative, which means even if you have, say, a times b times 1 over c, since it's multiplication, we can multiply anything in any order. We do not have to multiply a times b first. I can multiply a with the 1 over c, then multiply the b. I can multiply the 1 over c with the b, then multiply by a. Or if I'd like to, I can kind of multiply them all together, create just one big fraction. Okay, that may help me. And kind of conversely to that, if I have just a bunch of things being multiplied in a fraction, we know we can split these up into multiple terms being multiplied together. Might help with our simplification. Okay, and that's a over 1 times b over 1 times 1 over c times 1 over d. We can multiply the numerators together, the denominators together, and we get a times b over c times d. All right, so we're going to use that. We also remember all of our trig identities. Cosecant is 1 over sine. Secant is 1 over cosine. It's important to know that if you have these in a denominator, if you have like cosecant in a denominator, that it's the same as sine in the numerator. Or if you have like secant over cosecant, it'd be sine over cosine. And just kind of flip the location and change it to its reciprocal. Cotangent is the reciprocal of tangent. It's 1 over tangent. However, knowing that tangent is sine over cosine, we can write cotangent as cosine over sine. Okay, finally, our very important trig identity, sine squared x plus cosine squared x. What does that equal? 1. Why? Where does that come from? Yes, and what is that called? Yes, the Pythagorean theorem. Thank you, Mr. Biagini. Yeah, Biagini. Okay. Not everybody realizes it. They just kind of take, okay, yeah, sine squared plus cosine squared equals 1. But like, where does that come from? It's important to know that, you know, in math, things don't just come out of thin air. They come from certain concepts. If this is my unit circle and I'm trying to find sine or cosine values, we know that we can create these right triangles. And we know that the sine of the angle is the vertical length. We know that the cosine of the angle is the horizontal length. What's the length of the hypotenuse of that right triangle? 1, it's the unit circle. Well, we know a squared plus b squared equals c squared. It's a right triangle. Sine squared plus cosine squared equals 1. Isn't that interesting? Okay, maybe if you've memorized the unit circle, but don't understand that it's like coming from SOHCAHTOA, you know, it's coming from the trig concepts, that might have been completely lost to you. But maybe now you do understand it. It's also important to understand that you can manipulate this to create your other kind of identities with ones involved. Like I could divide everything by sine squared x. And when I do that, sine squared over sine squared, that's a 1. cosine squared over sine squared, that's a cotangent squared. 1 over sine squared is cosecant squared. So that just pops up naturally. You do the same thing with cosine squared. Instead of dividing by sine squared, I'll divide by cosine squared, and I'll get tangent squared plus 1 is equal to secant squared. Okay? And know that we can add or subtract and move anything around to solve for a particular piece of this squared. Like sine squared is equal to 1 minus cosine squared. Certain things like that. Okay? So, with all of those tools now in our toolbox and our arsenal, we can tackle some of what I consider these tougher trig limits, where we can't just plug in the value and get a function value. This one is pretty much the easiest one of the tougher ones. We have the limit as x approaches 0, 3 sine x over x. Now the proper way to do this is to first maybe rewrite this using our properties of multiplication as 3 times sine x over x. Then using a limit property, we could say, oh, that's a constant, k, times a function. I could pull out the constant and multiply by the limit. I could pull out the constant 3, multiply by the limit. Now, I know that the limit as x approaches 0 of sine x over x is 1. It is a trig limit that I will know. And so I just have 3 times 1, and I get the answer 3. Now, this would be the proper way to get to the answer 3. However, in the future, you guys can just look at this and go straight here, understanding the properties and our special trig limit sine x over x as x approaches 0. Okay. We have another one. Again, my first attempt would be to plug in the value 0 here for t. If I plug in 0, I would get 0 over 0. Okay, what to do? Don't give up. Let's just try to simplify. In this case, it's very easy to manipulate things using your properties of multiplication. This is in parentheses, sure. This is kind of like our a times b times 1 over c. Well, since it's multiplication, I could just write this as a times b over c, and that's totally legal. There's no addition, so there's no distribution that needs to be done. So I'm going to write this as a times b over c. Now, the proper way to go from here is to say, oh, I have 2 functions. I have this function and this function. I'm trying to find the limit of that product. I should split this using my limit properties into 2 different limits that I will find and then multiply together. Now for this one, I would plug in 0. So I kind of find f of 0 and get the square root of 9, which is just 3. And this is my known one, which is 1. So my answer is 3. In the future, I'd probably expect you to get here, and then from here, get there. Yes? Next one, we have tan x over x. This is not something that we have known. This is something that we have to figure out. For this one, I would use just my trig identity knowledge to help figure this one out. I would, instead of using tangent, replace tangent with sine over cosine. and then simplify from there. Why don't you guys go ahead and do that and try to find this limit. I don't think you should be squaring those things. Just sine over cosine. I don't know. Why do you have it squared? What's that 2 there?
Oh, I was doing that.
Oh. Okay. That one's good. Go back to that one. There you go. This is correct, but then this is unnecessary. Since it's multiplication, you don't need a common denominator. You can just multiply things in any order. So the problem is you have 0 over 0. Simplify more. Simplify more. If you ever get 0 over 0, if you ever get 0 in the denominator, simplify more. It seems so easy, but kind of knowing the correct things to do here, a lot of people struggle with. Most of us can get here, okay? Use the fact that tangent equals sine over cosine to write our fraction as sine over cosine over x, which can be written as sine over cosine times 1 over x, using the whole division is the same as multiplying by a reciprocal. But if I plug in 0, I'd still get 0 over 0. Yeah, I'd get 0 over 1 times 1 over 0. It's the same as 0 over 0. So what can I use is my friend Mr. Multiplication, and the fact that since this is all multiplication, I can decide to take this x and multiply the 1 over x by the sine. And then I'll take the cosine and I'll multiply it by this 1. I'll just leave it in the denominator for something else. Turning this into sine x over x times 1 over cos x. So most of you were like on the right track, just weren't sure exactly what to do. And we use our properties of multiplication to just move things around. And we move things around so that I can find these individual limits, which can be found. Yes, this is 0 over 0. Yes. If I plugged in 0 here, I would get 0 over 0. However, you now know that this limit is 1. So we're just going to use that from now on. Sine x over x as x approaches 0 is 1. Just know that. That kind of removes the 0 in the denominator. So whenever we have an x in a denominator, put it with a sign so that you have sine x over x. Gets rid of that problem 0 in a denominator and allows you to evaluate things without always getting 0 over 0 every single time. Now the second limit, the limit as x approaches 0, I'd plug in 0 into cosine. The cosine of 0 we know is 1. It's the horizontal distance at that angle 0. So this is 1. So my answer is 1. Okay? We're going to try the next one. For this one, it's important to know that this notation sine squared x is the exact same as sine of x quantity squared. Mathematicians use sine squared of x so that they don't have to always write parentheses when they want to square a trig function. Okay? So this is sine of x squared. Now, the reason why they put it over the sine and not over the x is because when you typically put a square over the x like that, people will assume you are squaring whatever is inside the trig function. Okay? So it's important to understand the difference. And for this problem right here, we're going with this guy, not with this guy. So what I would do is rewrite this as sin x times sin x. Let everybody go from there. See if you can find this limit. Bless you. All right, check your answers with a neighbor. What did you and your neighbors get? Did you get the same thing? Okay, we rewrite it as sin x times sin x. We can split up this fraction into multiple pieces. I could decide to put the sin x with one of the x with one of the sin x's, and then the other one would stay. So this one is left over. So when I'd find the limit, I know the limit as x approaches 0, sin x over x is 1. But here, the limit as x approaches 0 sine is the sine of 0. The sine of 0 is 0. I have 1 times 0. That's not 0 over 0. 0 over 0 is different. 0 over 0 is undefined. 1 times 0 is just 0. It's just a number. Okay? You're not allowed to divide by 0, but we can have limits that equal 0. Okay? Try this next one. Tangent x over x secant x. Now, some of us will just immediately start rewriting. But let me just show you, for some of you, it might be easier if you just separate things out from the start, like that, and then rewrite, then combine. It's up to you. Yep.
Oh. Could I also do this? I like kind of move it.
Yep. Yep. Should end up with a sin x over x and a cos x over a cos x. Or like a 1 over cos x times a cos x. This guy is 1. I can plug in 0 into this guy. Cosine of 0 is 1. I get 1 over 1. Now, you can also cancel these cosines and just get 1 as well, but the answer becomes 1. Okay, they're kind of tricky, right? Some of you might be like, they seem very easy, but then when we start doing them, like ourselves, it's like, man, I have no idea what I'm doing here. But Mr. Messner makes it look very obvious. So it just depends on how much you need to practice, how quickly we're getting this. This one's very similar. Probably can skip it. I'll just do it quickly. You can write it as sine h over h times 1 over cos h. This is 1. This is 1 over 1. That's 1. Okay. So very similar. Let's try this guy out. Yes. We will have a quiz over this next class. We will grade the previous quiz that you just took. We'll go over this stuff. We'll quiz over this stuff. And then we will grade this quiz. So we got 2 quizzes to grade next class.
For this one, I kept it as tangent x by x if you know it's 1.
Now that you know that it's 1, then yes, you could do that. Yes. Yep. 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 Key is the 1 minus cosine squared. What is that equal to? If sine squared plus cosine squared equals 1, if I subtracted cosine squared, I get sine squared is equal to 1 minus cosine squared. So this guy right here, Mr. James, is the same as sine squared. That's how we start. Yep. Key to this is knowing that 1 minus cosine squared is sine squared. You just manipulate your Pythagorean theorem unit circle identity. Sine squared plus cosine squared equals 1. Sine squared is equal to 1 minus cosine squared. Just subtract cosine squared. From there, I would rewrite this as sine x times sine x over x sine x. That was such a bad line, it wasn't even recognized. There we go. And then I'm going to take the x and put it with one of the signs. And then I'll take the other sign, put it with the other sign. I've seen students kind of stop here and say, okay, this is 1, but this is 0 over 0. Well, whenever you get 0 over 0, that is an indication that you need to try to simplify more, right? We'll do the obvious simplification that sine divided by itself is 1, and then you don't have to worry about this, okay? And again, properly, you should be saying, oh, we have a product. I'll take the limit of each individual piece of the product. Okay? All right. So curveball at you. What if we have a number inside the trig function? What if it's sine of 3x over x? Okay. Well, we could take a guess. We'd probably get it right. However, to show you why it's correct, we got to go through a little bit of a procedure here. So sine of 3x over x, that's not the same as sine of x over x times 3. Everybody wants to say, can I just, like, using my properties of multiplication, take that 3 and plop it here? No. Okay, it's a trig function of an angle. It's not sine times 3 times x. It's different, okay? It is a function. Whatever is inside the function has to stay inside the function. So you can't do that. It would be improper. What I'm going to do is kind of similar to how we solve the trig equations, like sine of 3x is equal to a half. I like to replace that 3x with a y and solve for y, and then divide all my solutions for y by 3 to find my solutions for x. And I'm going to replace 3x with a u instead of a y, just because in the future, well into the future, we'll use the same kind of technique called u substitution. Far, far in the future. Okay, so whenever I see 3x, I'm going to replace it with u. That's going to turn into u. And whenever I see x, I can solve this equation for x. Whenever I see an x, I could just replace it with a 1/3 u. So instead of x, I'll put 1/3 u, 1/3 u. And let me just rewrite this again. 1/3 u approaches 0 of sine of u over 1/3 u. Okay, now we've kind of gotten rid of that 3 inside the sign. But we got some other stuff going on. Namely, I have this 1/3 in the denominator. Okay, if you wanted to split this up, it'd be sine u over u times 1 over 1/3. That's the same as times 3. Okay, that's nice, but we have one little problem. There's this limit as 1/3 u approaches 0. Well, this is where we get a little bit fancy. For 1/3 u to approach 0, the only thing that can change in the 1/3 u is u. Okay? So if 1/3 times some value has to approach 0, the value needs to get closer and closer to 0, correct? Well, understanding that kind of concept, that allows us to just say u approaches 0 instead of 1/3 u. 1/3 u approaching 0 is equivalent to saying u is approaching 0. They both have to get closer and closer and closer to 0, u in the situations. And then I have u approaches 0 of 3 sine u over u. We already did this problem just with x's, and we got an answer of 3. After all that. Now, you might be thinking, well, Mr. Messner, what if we took that 3 and put it outside? Wouldn't you get that same answer? Yes, you would. However, you can't. Does that make sense? Okay, good. You're not allowed to do this. Do you get the correct answer? Yeah. Okay, cool. Yeah, so you're not allowed to do this, but you get this. Okay? Cool? Okay. What is that telling you? What's that telling you is that on a quiz or on a test, if you just like, that's fine. You got the right answer. Okay? not that important actually in this class. It's important to understand this concept of introducing this substitution. Okay, this substitution we'll use in the future, and maybe for a future year, I will require students to show every single step along the way. But I didn't change up the quizzes for this year. So for right now, can you pull that 3 outside? No, you still can't. But the answer is still 3. Okay. So you could probably guess what the answer is to this one. Discuss with your neighbors what you think the answer to this one is. Take a guess.
I think you're wrong.
Well, this is a 4 over a 5. I could rewrite this. I could write this as 4/5 times sine 2x over x, right? And then I could go through the whole U substitution process and get the answer 8/5. Okay? So 8/5 is correct. Why do you have to know the U substitution process? Because you'll see it in the future. You'll see this one on your homework. This one involves, if you do your homework, this one involves multiplying the top and bottom by x over x. And it also involves the fact that x over sine x is equal to 1. When I multiply the top and bottom by x over x, you can split this into sine of 2x over x, which you know is 2. And you can split this into x over sine 3x, which you'll find is 3. Not a third. It is a third, actually. The answer to this is 2/3. Not important, just there's a lot of questions on that problem from past years on homeworks. This is our challenge problem for the day. I'd like us to try to tackle this one.
Okay.
I haven't done it in a while, so I don't know what the answer is. Well, let's see if we can figure it out. We know that challenge problems are important to know the answers to and how to get the answers to them. All right, I got it. I remember it. All right, instincts. What is the first thing we should do? Shout it out. Rewrite the tangent as sine over cosine. All right, good start. Who's got the next instinct? What do you think, Ms. Smith? Yeah, I got a fraction inside of a fraction, right? Why don't we combine are 1 and our sine x over cos x. So I would rewrite this as cos x over cos x. Okay, go from there. Did you get it? Very, very nice. All right, check your answers with neighbors now. We got to pop out a negative. It allows us to cancel that and that, leaving us with -1 over cos x. Now I'm not plugging in 0. I'm plugging in pi over 4. -1 over root 2 over 2, which is -2 over root 2, which is totally fine if you leave. You multiply the top and bottom by root 2, you get 2 root 2 over 2, which is just -root 2. All right, now you got something to do for me. Well, that was for me.